we're going to talk about one of the most important integration techniques, which is called the substitution rule. In general, the integration is very difficult, and if we are lucky enough that our integration contains the structure when we are going to have the function and the derivative of its argument, so the function is going to depend on another function, and we will see the derivative of this function as well, then we can just use the so-called substitution rule in order to integrate this. So the general idea here is to denote the g of x as the new variable u, let's say. Then we are going to take the derivative from both of the sides. So derivative of the g of x with respect to the x is going to be denoted as a g prime of x multiplied to the dx, because it's going to show us that we just taken the derivative with respect to the x is equal to, so now we're going to take the derivative from u with respect to the u, which is going to be equal to the 1, right, and multiply this to the du, because we've just taken the derivative with respect to the u. So basically we are going to substitute g of x as the u and g prime of x dx as the du, right? So du is equal to the g prime of x dx. And our integration is going to be simplified to the version of the f of u du. Then if we are able to integrate this, it's going to be its antiderivative, right? So antiderivative of this f with respect to the new variable u. Then again we are going to resubstitute this u with the g of x here. So this is how it works for the indefinite integration. So let's do a couple of examples for this case. So let's say our function, so integration is given for this function. So square root of x squared plus 1 multiplied to the 2x dx. So if you look to the structure, so this function is very much looking for this one, right? So I've got a function which is going to depend on this one, so x squared plus 1. Our function f is going to be square root of something, right? And the derivative of the g of x, so derivative of this function, x squared plus 1, is going to be 2x dx exactly, right? So I've got a function and its derivative inside the integration. It means that we have to use the substitution rule in order to integrate this. So basically our u is going to be x squared plus 1. Then we're going to take the derivative from both of the sides of this equation. So the derivative of the u with respect to the u is going to be 1 multiplied to the du. And the derivative of the x squared plus 1 is going to be 2x. We have to multiply this additionally to the x because it shows us that we've just taken the derivative with respect to the x. So we are going to now substitute 2x dx with the du, right? And x squared plus 1 as the u. So let's substitute this back to here. It's going to be the integration of the square root of u multiplied to the du. So we just need to integrate this function. So it's basically the power function, by the way, u in the power of 1 over 2 du. And we're just using the formula of taking the integration of the power function. It's going to be u in the power of 1 over 2 plus 1 over 1 over 2 plus 1 plus some constant c, which is going to be 2 over 3 multiplied to the u in the power of 3 over 2 plus the constant. If you want, you can just bring this function to here, and you can write this as a 2 over 3 multiplied to the x squared plus 1 in the power of 3 over 2. So you can write this as x squared plus 1 in the power of 3 over 2 plus some constant. So please note, since we are doing this for the indefinite integral, so we need to always add some constant at the end. So let's do more examples. So I've got this function here, and according to the structure, again to the structure, so I see a function and its derivative here, right? So in our case, the function is going to be x4 plus 2, and its derivative is going to be x cubed multiplied to the dx in some form. Okay, so let's try to do this. So the u in our case is going to be x in the power of 4 plus 2. Then again, we are going to take the derivative from both of the parts of this equation. Left hand side should be taken with respect to the u. The right hand side should be taken with respect to the x. So it's going to be du is equal to the 4x cubed dx. right? So now we just need to figure out how to substitute all the things here. So basically, I just have x cubed multiplied to the dx, while my du is x cubed dx multiplied to the 4. So whenever your du is differentiating from the function here by some constant, it's very easy to deal, right? Because I can just simply put 4 here, right? Then it becomes exactly du, right? 4x cubed dx is going to be du. But since I multiplied everything to the 4, I can always divide this to the 4. Okay? So let's substitute everything here. So the cosine of x4 plus 2 is going to be integration of the cosine of u, right? 4x cubed dx is going to be exactly du. But additionally, we have to multiply this to the 1 over 4 because we additionally multiplied everything to the 4. So integration of the cosine of u is going to be simply 1 over 4 multiplied to the sine of u plus the constant. Then again, we're going to substitute this u with x4 plus 2 back to the function, back to the answer. It's going to be 1 over 4 sine of x4 plus 2 plus some constant. Let's do another example. So example number 2. Again, we're given some rational function. We need to figure out whether we have here the function and its derivative. So, like when I looked at this function inside here, I see that I've got a function 1 minus 4x squared. Then its derivative is going to be minus 8x, right? So I have similar thing here, x dx actually, right? So I don't have minus 8, the coefficient before the x. But we've seen in the previous example that it's very easy to deal with this problem. So we are going to denote the u as the 1 minus 4x squared. Then again, we're going to take the derivative from both of the parts. It's going to be du on the left hand side. Then we're going to take the derivative on the right hand side, which is going to be minus 8x dx, right? So again, you see, so I've got this minus a dx is going to be equal to the du, but here I simply have x dx. So I have to make it minus 8, right? If this would be minus 8, then I would just substitute everything here with the du. Since I'm multiplying everything to the minus 8, I have to divide everything to the minus 1 over 8 as well, because this minus 1 over 8 and minus 8 are going to cancel each other, and I'm going to have the same integration as the initial one. So it's going to be minus 1 over 8, the integration. So the numerator now is going to be simply du, and on the denominator we're going to have here as square root of u, right? I'm going to rewrite it slightly different form in order to integrate this much more easier. It's going to be 1 over 8 integration of the u in the power of minus 1 over 2, right? So we know that the square root of u is 1 over 2, and we have to put the minus because this u is on the denominator. We have to integrate this with respect to the u now. It's going to be equal to the minus 1 over 8 u in the power of minus 1 over 2 plus 1 over minus 1 over 2 plus 1. So minus 1 over 2 plus 1 is going to be plus 1 over 2. Whenever it goes up, it's going to be simply with a 2. It's going to be minus 1 over 8 multiplied to the 2. So this 2 actually coming from the denominator here, multiplied to the u in the power of plus 1 over 2. So it's going to be minus 1 over 4 u in the power of 1 over 2. And now we're going to resubstitute this back. It's going to be square root of 1 minus 4x squared divided to the 4 with the minus sign plus some constant. So now the conclusion is that whenever our function, or the derivative, differentiate from the du by just some constant, we can always deal with this by just multiplying this constant and dividing this constant in order to keep the balance in our equations. So let's try to do this example, which is not so obvious at the first glance. So we know what's the derivative of the tangent, right? But so the derivative of the tangent of x is equal to 1 over cosine square of x. And we actually get this formula using so-called quotient rule. So what's the integration of the tangent? So first of all, we need to rewrite the tangent in the form of the sine of x over cosine of x dx. And again, I just would like to ask you a question. Feel free to just pause this video and try to figure out what's going to be the u and the u. So we just need to use the substitution rule here. So I see the function on its derivative here, actually, right? So the cosine is going to be some u, and its derivative, sine of x dx, is also here, right? So the substitution rule is going to be introduced in this way, as the u is going to be cosine of x, and du is going to be a derivative of the cosine, which is sine of x multiplied to the dx. Again, so the sine of x dx was the minus is equal to the du, so I have to put here minus. Okay, so since I'm putting this minus, just because this du is going to fit to my integration, I have to multiply this to minus again, right? So this minus and minus are going to cancel each other. So we are going to have the integration with the minus now, du divided to the u. So the integration of the 1 over u, or 1 over x, is going to be simply ln of u, right? Plus the constant, so this minus 1 can go to the power of the u. It's going to be ln of u in the power of minus 1, right? Plus the constant, and now I'm going to resubstitute this back. It's going to be 1 over cosine, ln of 1 over cosine of x, because no matter what is the number, it's in the power of minus 1. It's going to be just the reciprocal of this number. So plus the constant, and we know that 1 over cosine is a spatial trigonometric function, which is called as the secant of x. So secant of x plus the constant. So well, this is how we are going to use the substitution rule. So in order to do this, we need to always be able to see the function and its derivative inside the integration sign.